Bismillahirrahmanirrahim. Today we have a topic that is database normalization in relational database environment. So what normalization is? Normalization is a process which actually we apply on relations, and the output of that process is again relations, normally in a decomposed form. So whenever we apply normalization on relations where we have some sort of bad relations, or in other words, we can say a certain kinds of anomalies that might be insertion anomaly, deletion anomaly, or modification anomaly within those relations. So the advantage of having this process is that we can remove those anomalies, and we might have one or more decomposed relations. So it actually breaks the attributes of the relation. So normalization process which we apply on relations is based on certain normal forms, and these normal forms have certain definitions which we will follow in this lecture. And you can say that these normal forms are certain conditions as well, using keys and FDs. Whenever we talk about FDs, it means we're talking about functional dependencies. So condition using keys and functional dependencies of a relation to certify whether a relation schema is in a particular normal form. And if it is not in a particular normal form, what we do is we break that relation into two or more relations, which are normalized relations. So there are certain conditions which are relevant to those normal forms. And if we talk about normal forms, there we have first normal form, second normal form, third normal form, and similarly then we have B, C, and F, which is called Boyce-Codd normal form, fourth normal form, and fifth normal form. The first normal form is actually a relation, you can say is a definition which is related to basic properties of a relation. So we discussed in earlier lecture what are the basic properties of a relation as per the Codd, who basically given this definition of the relational model. So if you recall, that properties are that the columns are unordered, the rows are unordered, every record is distinguishable, we can have null values, and the fifth important part of this definition is that at each row column position we only have a single value. You cannot have a multiple values or a list of values. It means you can say the values are atomic, and that also refers to the atomicity principle. So that is the first normal form definition, and we have to just see whether is there any violation among the attributes of a given relation. Second normal form, third normal form, and DCNF. BCNF stands for Boyce-Codd normal form, which you can say is a specific or a special type of normal form, or a special case of normal form, which third normal form. So based on the keys and FDs of a relation schema, which we will see. Fourth normal form we will also discuss. That is basically based on multi-value dependency, and we explain this concept as well. So there are certain additional properties as well. We have also fifth normal form. So we start our discussion with the first normal form. So first normal form is actually believes that every relation must obey the basic properties of the relations, and it disallows the composite attributes, multi-valued attributes, nested relation attributes whose values for an individual tuple are non-atomic. It means that has multiple values or a list of values, and that has a relationship with the other relation. So these are the things which we have to see and overcome whenever we have certain relation. And that is basically a definition of first normal form. So here we can see the definition. We have seen the definition. Now here is one example. And in that example, let's assume that you can see over here. These are the attributes of a relation called department, department name, number, department manager SSN, and locations. So according to this figure, that D number is a key, and from a D number, you can determine D name. That is the one FT we have. The second functional dependency is from D number, we can determine manager SSN. Yes, this is correct. And the other dependency is with the dotted line, and it says that D number can determine the location, but this says that it means here we have multiple values, and you can see in the B table as well. So we have some now records in that department relation, and in the first row you can see that there are 3 locations: Bel Air, Sugar Land, and Houston. So here research department is located in Bel Air, Sugar Land, and Houston. So it means that the 3 locations are listed here, and it violates the basic property which we have discussed earlier on in the case of first normal form. So what we can do, what option we have? So whether it is good to break this relation, or whether we can opt for another solution, that is that we can combine D number with D location as a key. Here you can see the D number and the location as a key, and in that manner, now we have 5 records in the department relation. But this relation, you can say, that is C. Here we have 5 records, but you see that there is no duplication of record. There are no composite attribute, and there are no multi-values. So it means that you can say that given these dependencies, we have the given relation department, which is unnormalized, having certain anomalies. And now in C, we can observe that that problem is resolved. Similarly, another example, if you see this particular example, here we have a relation that is called employee project, where we have SSN number, that refers to an employee SSN number, his name, project number, hours, which is related to project. So here we populate this table with certain values, so you can understand that what kind of anomalies are here. Here you can see that this SSN, the SSN over here, here we have a single value, then we have the employee name. Here you can see that there are 2 values, 1 and 2. So this is sort of a nesting. So, and also if you see the number of hours, here again you will find that there are 2 values. Similarly, if you see the SSN 333, 44, 55, here you can see 2, 3, 10, and 20. It means this employee is working in project 2, project 3, project 10, and project 20, and giving 10 hours each. So here, this is some sort of a nesting within a relation. So this is unnormalized, as we have discussed in the case of first normal form. So what we can do, we have one dependency here, that from SSN name, we can determine ename. So SSN and ename can be separated. And the other thing is that we have the P number. So if we combine that P number with SSN as a primary key, here you can see SSN and P number, because hours is dependent on both, not one of them. So hours, number of hours basically explains that which employee works in which project. So therefore, that depends on both the attributes. So it means that will become the key, and the hours will be replaced over here. So in that manner, you can say that what you did is that you observe that this relation violates first normal form, and you have actually converted it into 2 relations, or you can say you have decomposed this into 2 relations. Now we can have a definition of second normal form, uses the concepts of FDs in primary key. Here is the concept, or you can say a basic definition, that an attribute that is, first of all, we try to understand what prime attribute is. That prime attribute refers to an attribute that is a member of primary key. And full functional dependency means that whatever dependency we have, that attribute must be dependent on the composite attribute. So wherever we have this concept, full functional dependency, remember that we are mostly referred to an attributes, a group of attributes, which combines together and determine the value of another attribute. So the full functional dependency means, and the value of the attribute must depend on the whole attribute, not the part of the attribute. For example, that SSN number and P number determines hours. So both of them dependent hours. So hours cannot be only find out by P number or only find out by SSN. So it is, you can say that hours is fully functionally dependent on SSN number and P number. But in the second example, here you can see that dependency given is that SSN comma P number implies ename, which is not fully functionally dependent. Why? Because actually ename is dependent on SSN, not the P number. So it means it is dependent on part of the key, not the full key. That is basically the basic essence of second normal form. So you can say the relation is in second normal form if every non-prime attribute A in R. Non-prime attribute A in R means all those attributes which are normally called non-key attributes are not the part of the key, are fully functionally dependent on the whole key, on the primary key. So whenever we talk about second normal form, it means that we refer to those attributes which are called non-key attributes, and we'll see whether they are fully functionally dependent on the primary key or not. And if it is not the case, then again, the process actually breaks the relation or decompose the relation. So here we have an example. Let's see the example. Here we have a table called employee project, and you can see certain attributes: SSN number, P number, hours, ename, pname, and P location. So here the dependencies are given, and you can see that SSN number and P number combine together and determine hours. SSN number determines ename, P number determines P name, and P number also determines P location. So here, these are the given dependencies. So now, without populating the table, so if we have those dependencies, obviously there is a violation. And the violation is that hours is dependent on both, but ename is not dependent on both. P name is not dependent on both. So it means that there is no full functional dependency, and there is a violation in the case of second normal form. So what we can do, okay, let's see. So hours can be combined with SSN and P number. So here that will become the key, as this become a separate table. From SSN, we can determine ename, we can put it in a second table. And the third table is P number, P name, and location. So here, all dependencies are preserved, which is very important property, because as you know, that in normalization, we have to see that whenever we are applying the process, whether the two given definitions are obeyed or not. And two definitions are lossless decomposition, number one, and number two is preservation of dependency. So here all dependencies are preserved, and now we have these three relations which are in second normal form. Another example, you can see here that we have a table employee department. Here we have a detail about employee and department, including E number, SSN, birth date, address, D number, D name, and manager SSN. Here you can see the dependencies. From SSN name, we can determine E name, we can determine birth date, we can determine address, we can determine D number. And from D number, we can determine D name. And from D number, we can determine manager SSN. So here, these two are actually dependent on this. Okay, not on this. So there we have a D number and D name and D manager SSN. And similarly here we have, so this in this problem, if you see this table here, we do not have a combinational key. So here we have a single key. So whenever we talk about a single key, here the second normal form doesn't apply actually. Here we talk about third normal form. So it is better to have a little concept of third normal form, and then we can see the example. So third normal form, you can say a normal form where we see that whether the attributes given in a relation are not having a transitive functional dependency. If they are having a transitive functional dependency, then it means that the third normal form is not obeyed, and we have to see that whether how we can break that relation to have decomposed relations. So here we can see in this sort of relations, for example, FDX implies Z. It means X determines Z, that can be derived from two FTs from X to Y and Y to Z. So in that manner, we can say that we have that dependency. So it then actually X not directly determines Z. X determines Y and Y determines Z. So this is called transitive functional dependency. For example, here you can see this B example. Here we have a single attribute key. Therefore, remember, second normal form is not applied. So whenever we talk about second normal form, the key should be combinational, whether it will be two attributes or more than two attributes. So here, this problem is actually related to third normal form, because SS number determines D number and D number determine D name. So there is a transition. This is called transitive dependency. So what we do, we break the relation into two. One table represents the SSN, birth date, address, e-name, and D number. And the second table represents D number, D name, and manager SSN. Similarly, we can see other examples as well, where we have the same cases, as we have discussed about third normal form. So here you can see that there is another concept which is very important whenever talk about third normal form, that whenever we apply third normal form, we have to see that whether in the given relation there are candidate keys or not, because that is one thing where we have to be careful about it, because normally that creates an issue whenever we talk about those relationships. So that is the concept of third normal form, and you can see here. And if you go further, you talk about another concept which is called the Boyce-Codd normal form. And Boyce-Codd normal form is actually, you can say, is a specialized form of third normal form, or you can say the specialized case of third normal form. So for that purpose, there is a concept of a candidate key which we have to understand. What is a candidate key? A candidate key is a key which can have the characteristics of the primary key, but it is not the primary key. So what are the characteristics of primary key? The primary key characteristics actually are that they are unique and not null. So if any other attribute which can distinguish those records but not be the part of the primary key, then what we can say is alternative or the candidate key. So here we have why we want to have this concept, because this leads to another important aspect or a definition which is actually related to Boyce-Codd normal form. So you can say that alternative definition of third normal form is that we can create a relation schema R in third normal form if every non-prime attributes in R meets both of these conditions. It is fully functionally dependent on every key of R, and it is no transitive dependency on every key of R. So this is basic concept of third normal form. A relation R is in Boyce-Codd normal form if whenever A holds in R, then X is a superkey of R. Each normal form is strictly stronger than the previous one. So remember that second normal form is stronger than first normal form. Similarly, third normal form is stronger than second normal form, and similarly BCNF relation is stronger than third normal form. So there exist relations that are in 3NF but not in BCNF. So that might be possible that in some cases the third normal form definition cannot be applied, but the problem is that it obeys the third normal form, but actually it violates the Boyce-Codd normal form. So therefore we can say that BCNF is stronger than 3NF. So here we have one example here, that we have a property ID, which is a primary key, the county name, the lot number, and the area. And see the FDs. So FD says that from property ID, we can determine county name, property ID, we can determine lot number, property ID, we can determine the area. And county number and lot number both combine together and determine the property ID as well as the area. And area determines the county name. So here we have certain alternatives, but there is no violation of transitive dependency. So therefore, we can say that the relation is in third normal form. But there is one problem. Why? What is the problem? That there are certain candidate keys in the relation, as we have observed. So what we can do is that we can separate area as county name in a separate relation. You can see here. And what we can do, property, area, and lot can also be separated. So here in this manner, the property idea, area, and lot comes in this relation. And lot, in this particular table, we have the area and the county name. And how this happens? This happens by using the option which is here, that let's suppose if we have A and B and C, so and if A and B determines C, and similarly C can determine B. So this is sort of a relation where the third normal form applies. It means it follows the third normal form, but again, there is an issue regarding B, C, and F, and we have to decompose these relations further. So in that manner, we can apply this relation. See here, one example of B, C, and F, that we have a relation which is populated by some tuples. Student, course, and instructor are the attributes, and you can see 1, 2, 3, 4, 5, 6, 7, 8, and 9 records are here. And you can see that what is the relationship between course and student, student and course, course instructor, similarly from instructor and course. So here, this is in third NF because it is combined together, it's a key. So from student and course, we can determine the instructor. Similarly, we can have alternative combinations. So therefore, it is in a second normal form, but this relation is not in B, C, and F. So okay, the two FDs exist in the relation is that from student and course, we can determine the instructor. So it means if I know the Smith and database, so we can determine the instructor. Smith and operating system, we can determine the instructor. And FD2 is that we can determine from instructor the relevant course, from instructor mark to database. Yes, we can do this. Navadi database. It means that dependency is here. So this follows this rule where we have A and B are the keys and C is the third attribute. A and B determine C and C determines B. Same thing is happening here in this relation. So what are the options? The options are that we can break this relation into further. Relation not in BNSF should be decomposed so as to meet this property. So what we can do is we can decompose this, and there are three possible decomposition in this case. Whether you can have two tables, one is student instructor, and second is student and course. Second is student course and instructor as a primary key, and the second table is course and student, and the third option is instructor and course and instructor and student. All three combination will lose FD1, so we have to settle for sacrificing the functional dependency preservation, but we cannot sacrifice the non-additive property after decomposition. So out of the above three, only the third decomposition will not generate spurious tuples, the tuples which we do not require. So therefore, we go for the third option. So in that manner, we can apply the Boyce-Codd normal form to the given relation. Thank you so much for your listening. And we have followed this book, which is called Fundamental of Database Systems. The authors are El Mesri and Navadi, 7th edition. Thank you so much.